How space-time works. As inhabitants of Earth, we take space for granted. From our vantage point, space is a region that is located roughly 100 kilometers above the globe and in which there is no oxygen to breathe or light to disperse. After that, there is only emptiness, right? Time also passes by without stopping. It's not quite that easy. One thing that physicists have discovered over the past century is that space and time combine to generate a system that is so incredibly complicated that it may challenge our ability to comprehend reality. Hence, in this video, let's examine the elements that make up space-time. Both the size of space and the characteristics of space-time itself are enormous. We are aware of its warping and curvature, but what exactly makes it up? Just 5% of the cosmos, according to calculations by astronomers, is made up of baryonic particles. Dark matter and dark energy make up the remaining 95%. Other from monitoring their impacts, we still don't know much about them. Although it appears to us that space is empty, this is untrue. The diameter of the observable universe is 46.5 billion light-years. Our universe has been around for 13.8 billion light-years. We have evidence for all of this because we have observed the light that has traveled from far-off galaxies all the way back to the Big Bang. During the Big Bang's afterglow, the cosmic microwave background radiation provides information about the early cosmos. Therefore, even though space is a vacuum, it is not empty. The emptier portions of our universe are filled with gas, interstellar dust, and other small pieces of matter, while the denser regions are home to planets, stars, and galaxies. We cannot, however, be certain that our universe is the only one that exists. What lies beyond the observable cosmos is unknown to us. What, though, is dark energy? What is this enigmatic force that accounts for around 68% of the cosmos as a whole? Early in the 20th century, scientists were certain that the universe's expansion had to slow down over time. They reasoned that the expansion would slow down as the energy density would drop and gravity would take over, similar to how a ball that is thrown into the air eventually touches the ground. But Hubble saw that distant galaxies were drifting far apart from one another in 1929 when he turned his telescopes to the sky. The well-known Hubble law was then stated. It states that every far-off galaxy is separating from the others at a velocity proportional to its distance. The velocity at which a galaxy is moving away increases with distance. Everyone found this concept to be puzzling. Similar to throwing a ball up in the air, it keeps speeding up and finally moves away from us in space rather than settling down and returning to the Earth. We would think there is an unseen force at work if we saw anything similar with the ball. It was found by primarily 3 astronomers, Adam Rees, Saul Perlmutter, and Australian astronomer Brian Schmidt, who won the Nobel Prize in 2011 for their work. Scientists termed it dark energy. That is the most significant scientific discovery in history. Scientists were shocked to learn about dark energy and how it accelerates the expansion of the cosmos. By using the Planck telescope to map the cosmic background radiation left behind from the Big Bang, we have calculated the rate of acceleration. The Planck mission's final data, which were made public last month, confirm that dark matter and dark energy must exist, even though we don't know what they are. Know of how quickly humanity may travel in the future, we will never be able to reach anything else because everything but our nearest neighboring galaxies will have drifted out of reach. There are more questions than answers regarding dark energy. We are aware of how dark energy influences the universe's expansion, thus we know how much of it there is. Everything else is a complete mystery. The idea that dark energy is a quality of space is one way to explain it. The first person to understand that nothingness does not exist in empty space was Albert Einstein. Amazing characteristics of space exist, many of which are only now being fully comprehended. Others speculate that space may even be limitless. What, however, is in this area? Almost everything in the universe is made of hydrogen, with the exception of planets, stars, comets, asteroids, dust, black holes, and a few other items. Hydrogen is omnipresent. It's the lightest element to exist. It can be found anywhere from hot, dense star nurseries to the frigid and empty gaps between the galaxies. As Harlan Ellison wittingly stated, the two most common things in the cosmos are hydrogen and stupidity. Hydrogen is the most plentiful element in our universe. But what about the gap between hydrogen atoms? What is a vacuum of space made out of? Here's where I would have to call quantum mechanics and things get extremely crazy. Richard Feynman said, "I think I can reasonably say that nobody knows quantum mechanics, and that's quite true." On the absolute smallest sizes, it appears there is minimum resolution to the universe, called the Planck length. On these scales, the world appears to be a bizarre quantum foam, with virtual particles popping in and out of existence obeying the laws of quantum mechanics. No matter how contradictory this sounds, we can really test the effects of quantum physics in the laboratory, for example, the Casimir effect. If you position two very thin plates only nanometers apart in a vacuum, classical physics might tell you that the space between them is empty. However, the sea of virtual particles promised by quantum theory is impacted by the boundary of the plates. Fewer virtual particles can be formed in this narrow constricted zone than on the outside of the plates. This vacuum energy might actually be the key to comprehending dark energy of the universe on the biggest of sizes. Quantum mechanics is our deepest, most comprehensive approach of understanding reality. Yet the trouble emerges when trying to understand quantum mechanics. Honest physicists admit that we don't completely comprehend quantum mechanics. We have a recipe that we are taught in our textbooks, but we don't exactly know what's going on behind the scenes. That was all about space and what it is composed of. What is space-time? Space and time are like the opposite sides of the same coin. The famed physicist Albert Einstein had invented the idea of space-time when he combined these concepts in the theory of relativity. In simple terms, we all know about the three dimensions of our 3D world: length, breadth, and time. Einstein connected it with the fourth dimension, that is, time. We can stay at rest in space, for example, a man sitting at rest on his chair. Although we always travel through time in one direction, it never stops. According to our current knowledge of physics, space-time explains the extraordinary relativistic phenomena that emerge from moving near the speed of light and the motion of big things in our universe. Before Einstein had unified space and time, Newton's laws explained the motion of large objects, while Maxwell's equations described the qualities of light. But at the end of the 19th century, there was something peculiar about light that was troubling every physicist. Tests demonstrated that the speed of light was always constant no matter from which reference frame you observe. Around the same time, French physicist Poincaré theorized that the velocity of light might be an unsurpassable limit. Finally, Einstein drew all of these concepts together in his 1905 theory of special relativity, which stated that the speed of light was constant. For this to be true, space and time had to be united in a single framework that conspired to keep the velocity of light the same for all observers. Einstein, though, didn't reach the conclusion himself. The idea that space-time is a single fabric originates from German mathematician Hermann Minkowski in 1908, who remarked, "Henceforth space by itself and time by itself are condemned to waste away into mere shadows, and only a kind of unity of the two will sustain an independent reality." The space-time described by him is known as the Minkowski spacetime, which serves as the backdrop of computations in both quantum field theory and relativity. But how does spacetime work? Today, whenever people talk about spacetime, they commonly characterize it as a sheet of rubber or more often a fabric. This originates from Einstein, who understood as he developed his theory of general relativity that gravity was due to warps and bends in the fabric of spacetime. Huge objects like the Sun and Earth create distortions in spacetime that cause it to bend. These bends or curves constrain the ways in which everything moves in the cosmos, because everything has to follow the path along the curved spacetime's curvature. Motion because of gravity is actually motion along the curved spacetime. NASA really deployed a spacecraft called Gravity Probe B, which examined the form of the spacetime vortex surrounding the globe in 2011 and discovered that it nearly accords with Einstein's prediction. But still, much of it remains tough for folks to put their head around. Whilst we can consider spacetime as being analogous to a sheet of rubber, the comparison eventually breaks down. This is because the rubber sheet is two-dimensional and spacetime is four-dimensional. The warp is not just in space, but also in time. Despite its intricacy, relativity remains the best explanation for the physical phenomenon we witness. Nevertheless, there is a danger hanging over the horizon for physicists over the past 100 years. As noted above, the difficulty is to unite general relativity with quantum physics, which explains the properties of subatomic particles with high precision but does not incorporate gravity. Some theorists think that spacetime itself comes in quantized pieces. Some are trying to quantize gravity. Traditionally, when people talked about quantum gravity, they were referring to quantum discreteness, quantum fluctuations, and practically every other quantum phenomena in the book. We hope this challenge might be solved in the future by our scientists. But one thing that all scientists agree on is that empty space is very complicated. What do you think about spacetime? Can you try visualizing it? Let us know your opinions and questions in the comment area below, and don't forget to like the video and subscribe to our channel and press the bell symbol to be aware of future outstanding videos like this one.